हम्म, कैमरा ऑन कर लो।
सब
क्या ही फर्क पड़ता है। अहमद कहाँ भाग गया? Let's wait for a few minutes for people to join.
Okay, so we are starting the post-contest discussion. So, how did you guys find the contest? Was it too easy or too difficult? The problem. So, write it in the comments. Did you find the problems too difficult or too easy? I think most of you would have found too difficult because the standings were quite skewed. Like many of you guys have solved only two problems, while only single rate of you have solved three or four. So we would be discussing from problem A to problem G in that order. So without any delay, we can start now. Yeah, we are starting. A little too difficult. So like, which problem you found too difficult for its place? Like we kept this contest like a Dev 4 contest. So which problem you found too difficult? Okay, so we start the discussion by uh, starting with problem A. So problem A was made by Atif sir. So he would be explaining his approach to the problem and also show his model code. So over to you, Atif sir.
Yeah, Meher, can you put up my screen? Yep. Okay. So let's start with problem A. So just a second. I think it would be better if we start with the problem statement first. So I share my. Yeah, Meher, can you put it up again? Okay. So the problem statement says that we have been given an array machine which the operations are described as follows. You take the sum of all the elements of the array and take the remainder with the last element of the array, and whatever you get the answer you append it to the end of the array. Then you choose any number which was present in the initial array and remove it, restoring the length n, and you can use this operation any number of times till try to append a zero at the end of the array. So we have to find the minimum number of operations that will end the array machine or crash the array machine, whatever you want to say. So now the basic idea is that the number of operation will only be either one or two. You won't need any more than that. Now why is that? So consider the case one where the last element divides the sum. So the sum is when the sum is divisible by the last element. When you take the mod with respect to the last element, you will obviously get zero. So the array machine will crash at the first operation itself. So this is the trivial case. And the second case is when the last element does not divide the sum. So consider this example. So you have an array of length 5, 3, 1, 2, 5, 4. You'll get sum is equal to 15, and when you divide by 4 you'll get a remainder of, so let me write it separately to make it clear. You have sum 15, remainder is equal to 15 mod 4 is equal to 3. So you append 3 at the end of the array. Now what we can do is, you can see that whatever number was here will always be less than or equal to the length of the array, because given this the array is a permutation. Now what is a permutation? So permutation is basically a reordering of the numbers 1 to n. So it can be any reordering. So here we have all the numbers 1 2 3 4 5 occurring only once in the array. And so what you'll see is that whatever the last element will be, it will always be less than or equal to 5. So the remainder whatever you get when you divide it by when you divide the sum by with the last element will always be less than or equal to, will be less, actually strictly less than the number at the last element. So here you have 3, which is obviously less than 4. So now what you can do is, when you take the sum of all these elements and So now you take a new sum. So let's say sum dash is equal to 15 plus 3 is equal to 18. So now what you can do is take mod of what do you say, sum dash mod 3, which is the last element, the new last element which I have appended here. You get, what you get is equal to 0. So what you can do is you can just remove 3 from the array, and you'll end up with the new array being divisible by the last element. So in the next operation, it will be the second operation, it will go 0. Now why you will always find this case is because when you take the remainder with respect to 4, this will be something less, strictly less than 4. So, and yes, so in that case you get strictly less than 5. And so when you take the remainder, you can either remove the element itself if the remainder is 0, like in this case here the remainder is 0 with respect to the sum dash, or if it's not, it will always be something less than 3, which will always be present in the array because the array is a permutation. So you can easily see that the array machine can be terminated in two operations: when it is not, when the last element does not divide the sum, and when the last element does divide the sum, it will, the answer will be 1. So here the number of operations is equal to 1, and in this case you'll get number of operations equal to 2. So this is a very simple problem. So you just have to, so all you have to do is check whether sum divides the last element or not. When it divides, you get the answer as 1, and when it doesn't, you get the answer as 2. So I can show you a simple Python code here. So you have, we are iterating through the test cases. So I'm taking the input of the array A, and so the sum here can be directly calculated as n into n plus 1 by 2, because given the number, the array is a permutation and the length is n, so the sum will always be n into n plus 1 by 2. Now if sum is divisible by, so here I'm taking the mod, which is basically saying, checking if sum is divisible by a, the last element, which is a n minus 1, indexed by n minus 1, and if it is divisible you print 1, else you print 2. And similarly, if you want with C++, you can do the same thing. Here I have taken the sum iteratively instead of taking it directly, and I could have done n into n plus 1 by 2 here as well, but here I thought I'll show the other way. So here the same thing, I'm just checking if it is divisible. If yes, then 1. If it is not divisible, then the answer would be 2, and that completes the solution.
So, like many of you guys solved this problem pretty fast. So, I don't think there was any implementation related issue in this problem that you guys faced. So, we move forward to problem B. So, problem B was made by Raghav, but he is currently unavailable in the stream. So, the solution to problem B would be explained by Hamad. So, Hamad, I'm adding you to the screen.
So the problem B was this, that we had n teams and we wanted our team to win, and the first four teams qualified for the playoff. Now we could see, like, if we consider from the fourth team to the last team, there would be n minus 3 into n minus 4 by 2 matches between them, ignoring the first three teams. And by pigeonhole principle, there would be at least one team among these last n minus 3 teams that would win n minus 4 by 2, at least n minus 4 by 2 matches. And if n was even, then we could always construct a case in which all of the last n minus 3 teams win n minus 4 by 2 matches. And if n is odd, then we could go with like n minus 3 by 2 teams win seal of n minus 4 by 2 matches, and the rest n minus 3 by 2 teams win n minus 4 by 2 matches. So we could see, like, to get to the fourth position, at least there would be a team winning n minus at least n minus 4 by 2 seal matches to get to the fourth position. So and to improve position, we would have to win at more matches, or at least the same number of matches. So the minimum number of matches required to qualify for our team would be seal of n minus 4 by 2. Did anyone face any problems in this? Any doubts? What part could you not understand? Like, I'll try to go over it once again. There are n teams, and we had to only the first four qualify, and we wanted our team to qualify with a minimum number of wins. Now, here we are considering, like if we consider the last n minus 3 teams, ignoring the first 3 teams, there would be n minus 3 into n minus 3 C2 matches between them. We ignore the first 3 teams. Using this, we could prove that the fourth team would win more than equal to n minus 4 by 2 matches. This comes from the pigeonhole principle. Is this clear? Till now, it is all clear, right? Like the fourth team would win at least n minus 4 by 2 matches. Pigeonhole principle. Like you could see it intuitively also. There are n minus 3 into n minus 4 by 2 matches, and there are n minus 3 teams. So there would be a team winning at least n minus 4 by 2 matches. Ignore the principle. You can use your intuition here. Is it now clear? Yeah, that's right. So if the four team would be winning at least n minus 4 by 2 matches, and we could show using construction that in any case we could make the fourth team win seal of n minus 4 by 2 matches. In even case, all last n minus 3 teams could win n minus 4 by 2 matches, and in odd case, the fourth team could win seal of n minus 4 by 2 matches. So first we prove a lower bound of n minus 4 by 2, and then we show that such a case always exists. So the minimum number of matches to to qualify would be n minus 4 by 2, seal of n minus 4 by 2. Is it clear now? I think it's fine. We could go to the next problem.
Yeah, it is clear. So we move to problem C. So problem C was made by Tushar sir, but he is also not currently available in this stream. So Atif sir would be explaining his solution, and I would also comment on some common mistakes that many of you guys did in its implementation. Because like if you see the standings too, there are and on an average two wrong submissions per user on this problem. So yeah, we would also explain that. So first we start with the approach to that problem. So over to you, Atif sir.
Yeah, I'm audible now. Yeah. So let's start with the problem statement. So the question says that you have three positive integers a, r, and x. So you have been once again operations. So you have subtract 1 from x or subtract a into r power p from x for some non-negative. So you have the freedom to choose p in every operation. So there here you have two types of operation type 1. Let's say this is type 1, this is type 2. Find the minimum total number of operations required to make x equal to 0. Okay, so one can easily see that one way is just to subtract 1 x times and you get x is equal to 0, but we are looking for something better than that. So let's see what we can do. Okay, so let's consider, so we have been given the second operation is of the form a into r power p. Now consider the case when a is greater than 0, a is greater than 1. So you have something like 2 3 4 5. So one can see that in the second operation, anything you subtract will always be a multiple of a. So uh, at the end, you will have to use, like, for subtracting the amount x mod a, like whatever a leaves as a reminder when you divide x, whatever x leaves as a reminder when you divide by a, that cannot be subtracted using the second operation. So you'll have to use this first operation to remove those, which will be x mod a. Now, so you can easily see that the minimum number of type 1 operations will be x mod a. I hope this is clear. Let me just go through it again for clarity, just quickly. That if a is greater than 1, then you can see that uh, you will need minimum number x mod a operations, because at the end, if you how many ever type 2 operations you use, at the end you will be left with x mod a, at least x mod a, because you can't subtract those numbers which are not multiple of a and end up with 0 easily, because you will be going to negative numbers and they'll only increase the operations, and you can prove that easily. And oh yeah, you don't want to end up in negative operations, negative numbers actually, or else be you'll not be getting into to the right answer, x is equal to 0. Okay, so now when a is equal to 1, also this will apply, because when a is equal to 1, you can see that x mod a will be 0, and when a is equal to 1, you just have to subtract r power p, and when if you see r power p at p is equal to, yeah, so you have non-negative integer p, so at p is equal to 0, you'll have the same as type 1 operation when a is equal to 1. So this case applies for any case that the minimum number of type 1 operations will be x mod a. Now we can prove, now we are going to show a construction how we can use the type 2 operations efficiently, such that we have to use uh, the type 1 operation only x mod a times and no more than that. Now what we can do is consider, now if you remove x mod a, let's say x mod a is equal to y. Okay, now what if you remove the these y operations from x? So let's say x minus y, whatever the number is left, we are going to subtract, we are going to get this to 0 using only type 2 operations. Now if you see minus y will be divisible by a. So you can say a divides x minus y, because you're subtracting the remainder that a x leaves when divided by a from x. So the rest will be divisible by x. So let's say x minus y divided by a is equal to z. Let's say z. I'm going to introduce a lot of variables, so really sorry about that. But so yeah, so let's say, so this will be an integer, because as I said, a will divide x minus y. So now what you can see is, so let's, now we can actually, we only have to use operations where you subtract r power p, because I have already divided it by a. So I have to reduce z to 0 using, to reduce z to 0 using r power p operations, where I have the freedom to choose p. Now if you see, you can actually express z in the base of r. Let's say in decimal representation, you represent any number in the base of 10. So you write, let's say any number, let's say 732 is, let's say 732 can be written as 7 into 10 power 2 plus 3 into 10 power 1 plus 2 into 10 power 0. So this is the actually the most efficient way you can reduce 732 to 0 by, if suppose r is 10, you can actually use p. With p is equal to 0, you use it 2 times, and with p is equal to 1, you use it 3 times, and with p is equal to 2, you use it 7 times. You'll reduce it to 0, and it can be easily seen that you can't do any better than that. And the same applies to like if you consider binary, which will be at r is equal to 2. So if you consider base 2 representation of any number, you will do the exact same thing. So what you're doing is the number of type 2 operations will exactly be the sum. The best way you can do is with sum of the digits when you express it in that base. So when you have the base 10, you will do 7 plus 3 plus 2. That would be, if I present 12 operations. So this will require 12 operations with, let's say, type 2 operations. Type 2 operations with r is equal to 10. And this is for z is equal to 732, not x is equal to x minus y is equal to 7. This is for z, because we have excluded z a by dividing it by a from x minus y. So we only have to subtract r power p. So the same way, if you have base 2 representation, so you will take the you will take the binary representation of that number and take the sum of digits, which will be the number of set bits in that representation. So now we can go to the code and actually try to understand what we are trying to do here. So the first step would be let's introduce initialize answer with x mod a. So this is the number of type 2 operations. I'm going to write it here. Type 1 operations. And now what we do is divide x by a. Now here by a already excludes the remainder, because here we are taking the quotient of quotient what we get when you divide x by a. So it takes the integral part of the result, and you get, and that already, so this is basically x minus y divided x minus y by a. So this is what you get. So what we do is, when r is equal to 1, you do answer plus is equal to x, because when r is equal to 1, you are actually, you just have to, you are using, when r is equal to 1, when you divide it by a, you have to reduce z with just type 1 operation, because r for p, for any p, will be 1. So you are basically using type 1 operations on z. So that will be, so this is the direct case where you'll just add x. So here you can actually use z if you want, which is being replaced with x here. But yeah, so in the other case, when r is not 1, you would so here what we're doing is taking the modulo r. So this is actually taking the digit when you represent it in base r. So this is that's a basic algorithm for actually calculating it. So if you consider r is equal to 10, so let's say 732. So the first step with percentage, so mod r will give you 2. 732 mod 10 will give you 2. So answer will be, you will add 2 to the answer, then divide it by 10 and take the quotient, which is, so you get x is equal to 73. Then you loop again, you get, in the next step you get 3 as a reminder, and you add that to answer, and then you divide it by 10 again, you get 7. Then in the last step you add 7 to the answer. So basically this a loop adds the digits when you represent it in base r representation, and at the end you print the answer. So this is for type 2 operations. Operations, and the above one is for type 1 operations. So yeah, if you want, the same thing can be done in C++ as well. And so here, these are the type 1 operations, and this the if condition here, and the loop is exactly same, exact translation of what we saw in Python. I hope that is clear for everyone.
Uh, so I am just showing the common mistakes that some of you guys did in the implementation of this problem. So I am sharing my screen. Yeah, so like these were some of the common mistakes that you guys did for this problem. So some of you guys had to calculate 2 raised to I in your implementation. So you tried to do this by shifting 1 to the left by I. But the case is that when I is greater than equal to 30, you can't do this because it would be out of the integer range. Not 30, but around 32 something. So you need to do this in this way. One LL right shifted by I, left shifted by I means that the number is to be treated as a long and not as an integer. So you got overflow. Some of you got overflow due to using this. Then some of you used inbuilt functions like log, square root, and some others. And again, these functions behave like very weirdly for long numbers. And as you can see in the input to the problem C, the numbers were of the order 10 raised to 18. But integer maximum value is 2 raised to 31 minus 1 if we take signed integer. So that also results in overflow if you take for long if you uh, take these functions for long inputs. Then yeah, the third point is that some of you tried to store a value greater than 2 raised to 31 in a variable that was declared as an integer. So that again caused overflow. Then some of you tried to print the answer twice or incrementing the same thing twice in outside of a conditional statement and also inside a conditional statement. So that gave the double of the actual answer in some cases. And finally, the case that many of you missed was that the case r equal to 1, in which case if you use a simple while loop, like dividing the your variable by r every time would result in the same variable. So you need to treat the case r equal to 1 separately, and many of you got time limit exceeded on test 2 or test 3, I guess, for this mistake. So yeah, these were some of the like problems that you guys faced in implementation of problem C. Yeah, so let's discuss problem D then. Problem D was made by Haman. So he would be discussing the solution to this problem.
Is my screen visible?
No, it is not visible yet, Haman.
Is it visible now?
Uh, yeah, it is visible. Okay.
Okay, cool. So I forgot to share my screen last time. I'm really sorry for that. This was the problem D. Like we were given k, n jars of marbles, and there were some constraints on how many marbles we could take from each of them, and we had to take exactly k marbles. So I think first we should try to reduce this into a better form, and then we could try to
Ahmad,
find if
your code screen is not visible. The screen that you're showing for problems, the uh, StreamYard screen is visible to me only. Is your screen frozen, Hamad? Try to share it again. Yeah, open the problem window only now.
is it visible
Uh, you have not shared your screen yet. Like, I'm not able to see your screen here.
now?
Um, yeah, so can you open the problem statement?
I have opened the problem statement. Is it not visible?
Um, no, it is not visible to me. Can someone in the comments confirm this? So, are you able to see the problem? Um, just a minute. Huh? No, the viewers are not able to see the problem. Okay, try to turn your video off and then share screen.
Is it fine now? Is my screen visible?
Yeah, it's visible now, Hamad. You can continue.
Okay, fine. Like, yeah, I was talking about this. There are n jars of marbles, and we had to take exactly k marbles, and these are the restrictions on how many marbles we could take. So first, we should try to reduce this to a better form so that we could calculate BI directly. So that would be like first, I denote Li and Ri to be the minimum and maximum possible. Li corresponds to the left restriction and the Ri to the right restriction. We could calculate. We restrict Li to non-negative integers because negative amount of marbles doesn't even make any sense. So we could calculate Li to be maximum of 0 comma ai minus xi by I plus 1. Is this clear to everyone, or does anyone have any doubts regarding this? Like, you could use this inequality. I think everyone knows this. Like, ai minus xi by I would be less than ai minus xi by I c floor plus 1. So using this, we could get the left restriction would be ai minus xi by I floor plus 1, and the right condition would reduce to this: Ri should be equal to ai plus xi by I seal minus 1. So Bi should lie between Li and Ri. If Li is more than Ri for any I, then there does not exist any sequence satisfying these restrictions. So we could output minus 1 in that case. Is everything clear till now? Before we proceed further, any doubts? Okay, cool. So now we assume that Li is less than equal to Ri for all I, because we had already considered this case before. Now, since summation of Bi would be more lie between summation of Li and summation of Ri, so K should lie between them. If it lies outside this range, then also there does not exist any valid sequence. If all these conditions are satisfied, then we could find a valid sequence greedily. Like, if we iterate from 1 to n minus 1, and in each iteration we set Bi to minimum of Ri and K minus summation I plus 1 to j Lj. You could prove using induction that in this case Bi would always lie between Li and Ri. And like this, if we go to the next iteration, we decrease K by Bi, like the number of marbles that are left to take have decreased by Bi. And finally, when we reach the last case, Bn would be equal to the K that is left. An implementation detail in this would be like we could calculate summation I plus 1 to n of Lj using sums of suffixes. Uh, we could pre-process the sums and then proceed to calculating the BIs. Any doubts? I don't think there are any doubts, so we could proceed to the next problem. I was saying that we could calculate vi greedily.
Yeah, yeah, I got it. I was
We
just
set bi to
elaborating.
the maximum possible value. It could be at a particular I. We iterate from 1 to n minus 1. And if we could at max take to it to be ri or k minus summation of the minimum marbles we could take rest uh, from the rest of them. So minimum of these could be bi, and we could prove using induction that in this case bi would always lie between li and ri, satisfying the above restrictions.
Yeah, that's correct. So I was telling some implementation mistakes that some of you guys did for this problem. So we wanted that ai minus xi to be less than I times bi to be less than ai plus xi. So it can happen that ai minus xi is less than 0. So in that case, bi equal to 0 is a possible solution. So if you blindly do bi is greater than equal to floor of ai minus xi by I plus 1, then you might get a wrong answer, because floor of a negative number, like we don't want a negative number as our bi. So we want bi to be non-negative. So there is this one thing that you needed to take care of, that you need to check what the how the minimum value of bi changes on the sign of ai minus xi. And similarly, some of you guys did not take cases properly for ai plus xi also, that you took the maximum value of bi as equal to that in which I times bi was equal to ai plus xi. So that is also not allowed in this problem. So these were some of the edge cases in this problem, and if you are able to avoid them, then it's a easy AC solution. So yeah, that was this much for this problem, and we proceed to problem E. So problem E was made by Mridul, and he would be sharing his solution to this problem. So over to you, Mridul.
Um, One second, I'm trying to share my screen. Is my screen visible? Hello?
Yes, it's visible, Mridul.
Right. So this was a problem. We are provided with a geometric sequence and another number x. So we have to check for all its subsets of the terms, and we are provided with a property that if the sum of the elements of the subsets is less than or equal to x, then that subset is called valid. So we have to count the number of valid subsets. So here are the test cases, and here are the explanation for them. You must have read. So let's move on to the solution. So since each term is divisible by the first term, we can just simplify our initial problem by dividing each term by the first term and dividing x also with the first term. So we get a new problem with this as our geometric progression, and this y equal to floor division x upon a1 as our upper limit. So our aim is to represent every subset with a number, and we check all the bits in our number. I mean, we represent it in the binary format and check all the bits. So if the ith bit is from the back is on in our number, so we will include r to the power I minus 1 in our subset. So like if our binary number is 0, 1, 1, 0, then a subset would not contain 1, it would contain r, it would contain r square, and it would not contain r cube, and so on. So we have a claim that if any binary number x is less than another binary number y, then the subset represented by x will have some less than in the subset represented by y. So for the proof of that, we check the binary representation of both numbers. If the if y is greater than x, then both numbers will share the same prefix. I mean the same bits from the starting, from the higher side. So till a bit come which is on in y but not on in x. So let this be the ith bit. Since r greater than 2, we greater than equal to 2, we look at the sum, and this comes out to be this sum of geometric progression, which is less than r cube over I. So having the ith bit on is equal is will sum up to a number which is greater than having all the previous bits on. So the subset represented by y will therefore have a sum which is greater than the subset represented by x. So I mean, so this representation works like if this claim satisfies for this representation. So our final so we come up to a conclusion that we have to find the largest number less than 2 and that is the total number of subsets which represent a subset whose sum of elements is less than equal to I. Because for all the subsets which will be represented by a number less than that number, their sum will automatically be less than equal to I. So that can be done by looking at the base k representation of any number. If this is the base k representation of our y, we can represent this by int y equal to x by a1. So if this is the base r representation of our number y, we can write this number as 1 times r cube over 5 plus 0 times r cube over 4 plus 3 times r cube plus 4 times r square plus so on. So we have to find the largest number which is binary, and the sum of the subset represented by that number is less than equal to y. So if this is the base r representation of y, and we try to convert into the largest binary number whose sum should be greater than equal to whose sum should be less than equal to y, we land up to this number. This number is formed by first going from the highest digit to the lowest digit, and whenever we get the first digit which is greater than 1, we turn every further digit into 1, because using the same idea, this one, that r cube over I is greater than equal to r cube over I is greater than the sum of all previous bits, sum of all previous digits. So this was one greedy idea. This is slightly difficult ON approach. There is also another method to binary search on the range 1 to 2 power n minus 1. Means we can binary search on this largest number to get it and find our answer. Basically, our answer is the number we are looking for. So I just outputted that over here. For for the purpose of binary searching, we can set up a left limit equal to 0, means no number is in the given range, and another right limit to your n minus 1, because that is the number of maximum subsets that we have. So we do basic binary search while less than r, check for the middle number. For checking for the middle number, we go from 0 to n. If that bit is on in our middle number, we add the term in our sum, otherwise we just don't. So now we check if sum is less than equal to y. So all the numbers less than the middle number satisfy the condition. So we set L as mid. Otherwise, this condition is not satisfied. So we set R equal to mid minus 1. and in the end we just output our L because that's the number we have found. So, any doubts? You can view the code for a bit if you want.
Uh, if possible, enlarge the screen of the code.
Is it visible?
Yeah, it's visible now and more clear.
Clear. I guess we'll share the codes after the discussion is over. So, see if no doubts, then we can move on.
Okay, so this was problem E, and the one common mistake that some of you guys did the once we implemented this problem was the thing that I mentioned in problem C also was doing one left shifted by I instead of one LL left shifted by I. So again, in this problem, the inputs were of the order 10 raised to 18. So again, that is not an integer. So not an integer in the computer architecture sense. So yeah, so you can't do one left shifted by I to get the answer in this problem. So that's why many of you got a overflow error or runtime error or something like that on this. So moving on to problem F. Problem F would be explained by Hamad. So okay, Hamad, you can start explaining.
So this was the problem if you are given an array of non-negative integers of size n and a positive integer x, and we have to find the number of sets such that sum of the elements of the set equal x. So in this problem, it was a standard knapsack problem with a slight twist. Like we could see uh, in this problem, first we could ignore all the powers of 2 and now do a standard knapsack dynamic programming on it, and we could calculate number of ways to form number like DPI, where DPIJ would represent the number of ways of forming a sum of j using the first I elements. This is a standard way to solve knapsack problem, and like the recurrence would be this: DPIJ is equals to number of ways of the number of ways of forming a set of j by using the first I elements would be equal to a number of ways of forming j minus arri using first I minus 1 elements for plus dp I minus 1j, which is the number of ways of forming j using first I minus 1 elements. This would be the recurrence relation, and using this base case, we could find out how many ways would be to form subsets using the first n elements, such that there's some would be some integer less than equal to x. After that, we could add, while forming this, we ignored the powers of 2. After we did all this, now we could see that there would be a unique set of powers of 2 to be added to each value of j to make it equal to x. So there would be a 1-to-1 mapping. So we could just calculate dpn summation of dpnj for all j, and that would be the answer. Any doubts regarding this? I think we can see the code here. First, this P2 denotes the powers of 2, and this is the input, and this is the DP. This would be a base case, and if AI is not a power of 2, we increase I plus 1 using AI. If it is a power of 2, then we don't increase it using, we don't include AI, and we are modding at every step to make ensure that it does not overflow. And finally, the answer would be summation of DP and I, because each of them uh, can be increased to X using a unique set of powers of 2. Is it clear? I, I think we could move on.
Hello, was I not audible?
Now you're audible.
So I was telling that I, since some of you might not know what knapsack is, I have sent a link in the chats to as a reference to understand what knapsack is, and you can see it and understand. And this problem is very much based on the idea on the standard idea of knapsack. So okay, that's it for problem F. Since none of you solved it in the contest, there is nothing to say about implementation here. So the final problem G was made by me. So I would be sharing its solution and code now. Okay, so this is my solution to problem G. This may seem a little scary at first, such long solution, but the idea of this problem is really simple. So what we are given n strings, and we need to convert each string to a non-decreasing string. And we have been given some condition that if we replace some character of this string with some other character, like let's say I replace character A with character B, then I have to pay C of 0 rupees, like C of 0 because A corresponds to 0, B corresponds to 1, C corresponds to 2, like that. So I have to pay C of 0 cost. So I can do some operations of this type, like take some character of this string and convert it to any other character and pay some cost. And I need to convert the string to a non-decreasing string, and I want to minimize the cost. So this problem is based on dynamic programming. So we first, in the actual question, we have been given n strings, but the problem has to be solved individually for each string. So now suppose we are solving the problem for a string s of length m. So the first observation that we make is that the operations on any two distinct indices of this string, like if I'm replacing character at position I of this string, and then character at position j of this string, and again character at the position I of this string, then I could have just replaced the character at position I of this string twice, and then the character of position at the position j of this string. So the operations performed at distinct indices are independent of each other. So if we assume that x1, x2, xk moves are performed on the characters at positions i1, i2, ik, then we can perform x1 operations or on character position i1 first, then x2 on i2, and so on, till performing xk operation on character at position ik of the string. So the first claim is that it is always optimal to perform at most one operation at every position of the string. So why, like suppose we are changing character at some position x, let's say. So initially it had the character c0, and after a series of transitions, the final character at this position was ck. So we changed, like c0 goes to c1, goes to so on up to ck. So what was the cost of this operation? The cost of this operation was f of c0 plus f of c1 plus f of ck minus 1, where f of c denotes the cost of changing character c to any other character. That was given in the problem. Basically, the array c of size 26 that was given in the problem. I have just used the notation f here. So instead, we could have just performed the operation c0 to ck, and the cost would have been f of c0. That is, and f of c0 is less than equal to f of c0 plus f of c1 and so on, because f of c is greater than equal to 0 as given in the problem. So this claim 1 follows. So now coming to the dynamic programming part. So like let dp of x comma c denote the answer to the problem if we are solving for the string of if we are solving for the prefix of the string of length x plus 1. So basically if I have the string a b c d e, then dp of 3 comma a denotes that I am solving for the prefix of the string of length 4, and in the end I am forcing the last character of the string to be c. So then the answer to our problem is the minimum value of dpm minus 1c or all choices of character c. So is this clear till now? Uh, yeah, I don't see any doubts, so I'm proceeding further. Um, okay, so yeah, so it is clear till now. So now we need to find the minimum value of dp of m minus 1 comma c over all choices of character c. And what is the base case here? dp of 0 comma c equal to 0 if the first character of this input string was c, else it is f of s0, because we have been given in the problem that changing any character to any other character is only a function of the initial character, not the final character. So dp of 0 comma c is f of c0, f of s0 if c is not equal to s0. So now the dynamic programming claim is this. So for x greater than 0, dp of x comma c naught equal to minimum of dp of x minus 1 comma c, where c ranges over all characters less than equal to c naught. And by less than equal, and by comparison between characters, I mean that a is less than equal to b is less than equal to b, but c is not less than equal to b. So the if you consider the sorting of the characters according to the ASCII values, so then we are defining less than equal to greater than equal to according to that. So okay, so minimum of dp of x minus 1 of c over all character c less than equal to c naught plus fx of c naught, where fx of c naught equals the cost of making the x character of string equal to c naught. So it is equal to 0 if the initial character at position x of the string s was c naught and f of sx otherwise, using claim 1, because in claim 1 we had observed that it is always optimal to perform at most one operation on every position of the string. So now the proof of claim 2 is this. So if you are converting the string t into a non-decreasing string ending in the character c naught, then its second last character has to be some c is less than equal to c naught. And we also need that the string t prime, which is substring of size x now, so that also has to be non-decreasing. So if I ensure these two conditions, that the second last character is less than equal to c naught and the prefix of length x is also non-decreasing, then I get that prefix of length of x plus 1 is also non-decreasing. So then by the definition of dp, the minimum cost, so the way I define dp here above, so by its definition, the minimum cost to make t prime non-decreasing is a dp of x minus 1 comma c, uh, and the cost of converting the x character of the string, x is here 0 indexed, x character of the string to c naught is fx of c naught. So now we consider all possible values of c that were possible as the second last character. So considering all possible values of c, we can write that dp of x comma c naught is min of dp of x minus 1 comma c over all characters c less than equal to c naught plus fx of c naught. So that was the proof of claim 2. So we can get the answer to the problem by finding dp of I comma c in increasing order of I. and I would be showing the implementation of this solution. And the complexity of this solution is O of 26n if we take prefix minimum. So in case someone doesn't know what prefix minimum is, I would show it in the code. And if we avoid taking prefix minimums, the code is O of 676n, and that is also acceptable under the problem constraints. So here is my code. So I first take the t test cases. In the problem, it was stated as n, but here I take it as t. Just a minute. So I now take input string s, and I define an integer n to be equal to s size of s. Then I define a two-dimensional array int dpn26, and I first initialize it to 0. And then I take the base case I equal to 0. So for int j equal to 0 and j less than 26, dp of 0 comma j is equal to c of s0 minus a. But if j was equal to s0 minus a, then the cost is 0. So I just change that particular value to 0, and all other values are equal to c of s0 minus a. Now we start the dp. So for int I equal to 1, I less than n. So since we are taking 0 indexed, we are taking here I less than n and not equal to n. So initialize first a variable temp that is initially equal to infinity. I have defined infinity as 10 raised to 15 years. So that is quite large compared to the values that are used in this problem. So for int j equal to 0, j less than 26, define, you take temp equal to minimum of temp comma dp I minus 1 j. So what this is actually doing is temp is equal to minimum of dp of I minus 1 comma 0, dp of I minus 1 comma 1, so on up to dp of I minus 1 comma j. Like this is what we wanted. Here our j is c naught and our c are these values. So I'm taking the minimum among them that was seen in claim 2. So temp actually is getting modified to this over these for loops. So this is what I was calling as prefix minimums. Even though the temp is a minimum of j plus 1 variables, at a time you are only updating it with the minimum of only one variable. So this is what the idea of a prefix minimum is. So if j is not equal to si minus a, dpij is temp plus c of si minus a, else dpij is temp. So this dp goes on, and then I need to now output the answer. So also initialize the output answer to be infinity, and then let j run from 0 to 26, and answer equal to minimum of answer comma dp n minus 1 j. So n minus 1 because we have to find the answer for the final string. So and we take the all possibilities of what the final character could be, then we will just print the answer. So this was the solution to this problem, and I hope you like it. And there are also some bonus problems that you can try related to this problem, and this would be available to you in the tutorial. So if you don't have any doubts, we could close the stream. So any doubts, you can put them in the group now. So I don't think there are any questions. So we would be closing the stream. So thank you all. And okay, bye.